Section 5.4, exponential functions, differentiation, and integration. So look at the graph of f of x equals the natural log of x. It is increasing on its entire domain, therefore it has an inverse. And the inverse of the natural log function is called the exponential function. It looks like this. Let's remember, on the inverse, the x's and y's switch places. Whatever the property was, if my function is increasing, its inverse will be increasing, but the concavity switches properties. Now, our inverse properties hold. That means that when you compose a function with its inverse, you get the argument. So, example, if f of x equals natural log of x and f inverse of x equals e to the x, then when I take e to the x and substitute it into my function, I should get x. And this is because the natural log of e to the x means, let's remember, a logarithm is an exponent. It means e to what power gives e to the x. Now, since y equals natural log of x and y equals e to the x are inverse functions, we also know that f inverse of f of x, which would be f inverse is e to some power, e to the power of natural log of x would equal x. So these are really nice things to know. So the natural log of e to the x is x, and e to the natural log of x is x. So two very important properties. Natural log of e to the x is equal to e to the natural log of x equals x. And we can extend that. What if my function is a function where u is a function of x? So the natural log of e to the u is the same thing as e to the natural log of u, which is u. Now, you should know this from Algebra 2 and Pre-Cal. Okay? So writing the exponential functions as logarithmic or vice versa, remember a log is an exponent, is the equal sign. E to the negative 2 is 0.1353, which implies natural log of 0.1353 is negative 2. Log is exponent. Negative 2 is my exponent that goes on, since I'm using natural log, the base of e, and it gives me this. Also, natural log of 0.3679 is negative 1, implies that e to this power gives me that. All right, solving for x. E to the natural log of 2x is 12. Remember, e to the ln u is u. So e to the ln u. So my u is 2x, which is 12, so x is 6. Natural log of e to the negative x is 0. Remember, natural log of e to the u is u. So my u is negative x. Okay, so negative x is 0, making x to be 0. But we could actually think about our log properties. If I bring this exponent down, I now have negative x times the natural log of e. We know that the natural log of e is 1. And again, we still get the same answer. Now we are going to look at the graph of e to the x and its derivative. Okay, you will see that here I am asking the calculator to show me e to the x and then the derivative of that. And I've adjusted my window so that I'm looking at x from -3 to 2 on a scale of where the x scale is 1, meaning every tick mark on the x-axis represents 1 unit. And my y is going to go on the interval from -1 to 6, and every tick mark on the y-axis will represent 1 unit. So you can see that here is e to the x, follow the bouncing ball. We know when x is 0, I should be at the point 0, 1. And you can see that it has done that. Now I have asked it to graph the derivative in a thick line. And you can see it is point by point finding that derivative and sketching it. And look, it looks like it's right over itself. It looks like the derivative of e to the x is actually itself. Interesting. Well, I wonder what happens when I give myself an exponent of something like 2x. So let's look at that graph. Again, we are following the path, e to the 2x when x is 0, y is 1. There it is. And now I have the derivative coming across again in a thick line. You can see it coming right here. Oh, it's not laying on top of itself. Well, that's interesting. So the derivative of an exponential function is not always just the exponential function. It is using chain rule, the exponential function times the derivative of that exponent. Actually, there's one more step that I'm not going to tell you about today. I'll tell you about it in the next lesson. It kind of makes you wonder, well, why didn't I teach it to you here? Well, we'll learn it in the next couple of lessons. Okay? All right. So here's a cool little proof that gives us this. We're going to use the derivative of our inverse function from section 5.3. Let us remember that we have f of x is natural log of x and g of x is e to the x. We know these are inverse functions. Therefore, f prime of x is, we know, 1 over x. We know that. So the derivative of e to the x would be the derivative of this function here, which from 5.3 is 1 over the derivative of f of g of x. Well, g of x is e to the x. We know that this is 1 over f prime is 1 over x, so 1 over my argument. And guess what? That's e to the x. I'm recalling this property that we learned, that the derivative on an inverse is 1 over the function derivative evaluated at the inverse. I'm going to give you a minute to write all this down. Here we go. Find the derivative of each function. Let us remember, the derivative with respect to x of e to the u is e to the u times du dx times u prime. All right, so f of x is 1 minus e to the x. My u is 1 minus x. So my du dx is -1, meaning my u prime is -1. So f prime of x is e to the u times du dx. E to the 1 minus x times -1, which gives us this. Number 2, let's let g of t be e to the -1 over t squared. Now my u is -1 over t squared, which we can write as negative t to the -2. U prime is 2t to the -3, or 2 over t cubed. So g prime of t is e to the u times du dx. E to the u times du dx, and clean it up. How do we want to think about this one? Well, let us remember natural log of a over b is natural log of a minus natural log of b. And let us remember the derivative with respect to x of ln u is 1 over u times du dx, or u prime over u. So we're going to simplify this using our log rules first. Natural log of the numerator minus natural log of the denominator. Our u is going to be e to the x plus e to the -x. So our u prime is derivative of e to the x is e to the x. Derivative of e to the -x is e to the -x times the derivative of -x, which is -1, which changes that plus to a minus when I simplify. So fun times, here we go. So y prime is u prime over u. This is just a constant. The derivative of a constant is 0. Now let's see what we can do with that. E to the -x really means 1 over e to the x. So I can rewrite these two terms. And what makes this look terrible? Well, the fact that I have a compound fraction. Fractions in a fraction. So I'm going to multiply the top and the bottom by e to the x. When we distribute, I get e to the x times e to the x is e to the 2x. It's e to the x plus x, okay? And so I get e to the 2x minus 1 over e to the 2x plus 1. And there you go. By the way, if you didn't think of it this way and you thought of this as e to the x squared, what do you do when you raise a power to a power? You multiply them. So either way you think about it, you should get the same answer for e to the 2x there. All right, let's look at the next one. Notice that this one does not have that natural log in front of it, so I can't apply any natural log rules. So we want to rewrite this and think about this as 1/2 times the quantity e to the x minus e to the negative x. So the derivative y prime is, notice my notation, 1/2 derivative of e to the x is e to the x. Derivative of e to the negative x is negative e to the negative x times that negative makes it positive. What can I do with number 5 here? Well, I can use a log rule and simplify it. And what do I know about ln e? It's 1, and so I get x. This is actually y equals x. I haven't taken the derivative. All I've done is rewrite. So y prime is 1. If you want to know what's coming up and why you need to know these, you should look at page 109 in the lecture manual. You really need to know your log rules when we hit that section. All right, so let's take y equals natural log of e to the 2x. We're going to find the derivative. Remember, 2x can come down. That would be 2x times natural log of e. We know natural log of e is 1, so 2x times 1 equals our y, so y prime is 2. Another way to think of this problem, this is y equals natural log of e to the 2x. So the derivative with respect to x of ln u is u prime over u. U prime is 2 e to the 2x, and u is e to the 2x. Notice those will cancel, leaving 2. Another problem to look at is y equals natural log of e to the x squared. My u is e to the x squared. My u prime is e to the u times the derivative of u. My y prime, because this is natural log of something, is u prime over u. So y prime is u prime over u gives me 2x. Now you have a couple of problems that'll be in your homework that require you to use implicit, so I'm always going to be throwing those in so that you recall those properties. Okay, this is a very good multiple choice style type problem for AP exam. So here we have e to the xy plus x squared minus y squared equals 10. Your product is right here, so when we go to take the derivative of x times y, we're going to be looking at our implicit step. E to the xy is e to the u, and the derivative of e to the u is e to the u times du dx. We have a pattern. Our u is x times y. The product rule, du dx, is x times dy dx plus y times dx dx, which we know is 1. So du dx becomes this whole quantity, x times dy dx plus y. Now we're ready to take the derivative. And we have aloha going on here. A lot of horrible algebra. So, taking the derivative of this. The derivative of e to the u is e to the u times du dx, which we just found. Plus derivative of x squared, 2x, that's easy, minus derivative of y squared is 2y times dy dx. Derivative of 10 is 0. Let's go ahead and distribute the e to the xy across these parentheses. We can see that we want to combine our dy dx terms, so we're going to move everything that does not have dy dx over to the other side of the equation, factor out dy dx, and divide by its factor. That's very ugly. Now, how do we simplify it? Well, I see this negative negative here. If I factor a negative out of the numerator here, I can write this nicely. And if I've done that factoring work, then that negative can come in front of the whole fraction. Make sure you know these rules. Again, these are just rules of exponents. E to the a times e to the b is e to the a plus b. E to the a over e to the b is e to the a minus b. And e to the a to the b is e to the ab. Properties of the natural exponential function. Your domain is negative infinity to infinity. There's no number you cannot substitute in for x. The range is 0 to infinity. E to some power will never be 0 because e is about 2.71828. You cannot raise a number that is not 0 to any power and get 0, but it'll be a little bigger than 0. Okay. We know that f of x equals e to the x is continuous, increasing, and 1 to 1 on its entire domain. The graph is concave up on its entire domain. The limit as x goes to negative infinity is 0. The limit as x goes to infinity is infinity. Now, when you go to your calculator to enter an e to the x type function, it's important that you use e to the x, not e. You use e to the x function. And by the way, notice it's right next to your natural log function. We're going to graph y equals 1/2 e to the x. Let's think about e to the x. When x is 0, y is 1. When x is 1, y is about 2.7. You can see in the graphed orange dotted line, that's my parent function, e to the x. What does 1/2 do? It takes all these y values and divides them by 2. And here we're going to graph e to the x over 3 and natural log of x to the third. I'll bet if I were to take e to the x over 3 and substitute it right here, natural log of e to the x over 3 cubed, hey, guess what? That gives me x. So these are inverses. Here is e to the x over 3. Again, when x is 0, y is 1. And you play around with the values, and here is natural log of x cubed. Notice they reflect across the y equals x line because they're inverses. And now we get to a really fun problem that requires so much nice work, and that is finding our second derivative. Well, let's first of all recognize I'm going to write this g of x as x to the 1/2 plus e to the x times natural log of x, and we can see that for this step here, it's going to require product rule. Here we go. G prime is 1/2 x to the negative 1/2. We know how to do that. We're pros at that one. Here I have a product. E to the x times the derivative of natural log of x plus natural log of x times the derivative of e to the x. E to the x times the derivative of ln x plus ln x times the derivative of e to the x. There's our product rule. And I'm going to clean it up a little bit. Now this is the first derivative. I want the second derivative. So again, I'm going to revert to my exponential form for this term. I am going to have to do quotient rule for this term. And guess what? For this one, I did that right up here. All of this is the derivative of the product e to the x times natural log of x. So I already know what's going to go right here, all of that. But I have to do quotient rule here. So it gets messy. The derivative of this term, that's easy, it's algebraic. Quotient rule, low d high minus high d low over low low. X times e to the x minus e to the x times derivative of x is 1 over x squared. Plus, we already know all of this we found here is this. So I'm just going to substitute that in. Now you can see I have a couple of terms that don't have a common denominator. That's easily remedied by multiplying this one by x over x. That gives me an x squared in the denominator, and I can put these in one fraction. I can take this and algebraically clean it up, and there's not a lot I can do with that. Adding similar terms gives me 2x e to the x's minus e to the x over x squared, and there is your second derivative. Ugly. Okay, here's a fun one. This is going to continue onto the next page. It says, show that the function y equals f of x is a solution to this differential equation. Y double prime minus 2 times y prime plus 5 times y is 0. We want to show that this function for y will give me that when I take the second derivative, subtract twice the first derivative, and add 5 times the function. Or I could rearrange this like that. Well, there's just a whole lot of work going on here. So y prime is, this is a product. So e to the x times the derivative of this, derivative of cosine is negative sine of 2x times the derivative of 2x times the 3 that's there, minus derivative of this is 4 times cosine 2x times 2, there's your 8. That is just the first times the derivative of the second. I still have to do second factor times the derivative of the first. Now, here I'm going to distribute the e to the x, distribute the e to the x, add similar terms. That's one way. Or I could notice that both of these terms, this plus this, have e to the x as a factor. If I factor it out, this is what's left. I still get this. I still get that. Factoring a negative 5 e to the x out of here. All right, we're going to continue on the next page. If you want to write down what you have here, go ahead. Let me finish explaining this example before you write anything else down. Okay, here we go. So from the previous page. Now I'm going to go for the second derivative. Again, it's a product. So this factor times the derivative of this one plus this factor times the derivative of that one. And now we have aloha. I can distribute the negative 5e to the x across this, distribute the negative 5e to the x across that, and add similar terms. That is one way to do this. I could also, from here, see that I have a common factor of negative 5e to the x. If I factor out that negative 5e to the x, this is what's left inside. Adding similar terms, all of that becomes 5 cosine 2x. I still get the same answer. So easier for the win. Now let's remember what it was we were supposed to show. We were supposed to show all that. I need to take the second derivative, which is this, subtract twice the first derivative, add 5 times the original function, and show that I get 0. Here's my second derivative minus 2 times, there's my first derivative, and I went ahead and moved the 5y over here, equals negative 5 times, and here was my y. And now I'm going to show that the left-hand side equals the right-hand side. So the left hand, when I do the algebra, gives me this, which is what I have on the right-hand side. So we did it. I leave it to you to go to page 353 for extrema and points of inflection. Look at example 5. And now we're going to undo that derivative. So the integral of e to the x dx is e to the x plus c of frustration. So how about when I have e to the u? Well, I need du here. That's what I have to be sure of doing. And if I get the pattern e to the u du, that anti-differentiates to e to the u plus c. So let's look at the problem. E to the negative x to the fourth times negative 4x cubed dx. I want to integrate that. You will notice our u is negative x to the fourth. And our du is negative 4x cubed dx. I have exactly that. So I have exactly my e to the u du pattern. So I'm going to go straight to the answer. I'm not going to bother changing everything. I recognize this pattern. This is the important thing, recognizing the pattern. I have the pattern. It integrates to e to the u plus c. That looks pretty hard. No, you cannot cancel these. And I'm sorry about the condition on my page. I've spilled coffee on it a few years ago. Okay, so I have the integral of e to the 2x over 1 plus e to the 2x dx. If I were going to call some part of this u, I would probably call the denominator my u. And if that's the case, what is my du? Du is 2 e to the x dx. Look, I almost have it. So all I got to do is multiply and divide by 2 to get my du here. And you'll notice that I have 1/2, 1 over u, and there's du. I could also write that as, and if I have that pattern, notice 1 over u du is how we get the derivative of ln u. So the antiderivative is ln of absolute value of u with the coefficient of 1/2 in front plus c. And I can do a little bit with that. I have got to go in and substitute back what that u is. Notice how I don't need the bars. Why do I not need the bars? E to this power is always going to be positive, and 1 plus is positive, so I don't need bars here. Let's get a little more complicated. I still think I'm going to make my u this e to the x plus e to the negative x. So my du is e to the x minus e to the negative x dx. I have that if I factor the 2 out, so I'm going to just factor the 2 out. And notice I have du. Oh, what do I have? This isn't a ln u type because that is u squared. Oh, so this becomes 2 u to the negative 2, there's my du. We know how to integrate u to the negative 2. It's u to the negative 1 over negative 1. I'm going to bring that negative out in front. U to the negative 1 means 1 over u. There it is. If you want to write this down, go ahead. And our last example. Find the area of the region bounded by e to the negative 2x plus 2. Y equals e to the negative 2x plus 2, so we need to know what that looks like. Y equals 0 means the x-axis, x equals 0 means the y-axis, and the line x equals 2. So we can do this integral from 0 to 2, e to the negative 2x plus 2 dx. So again, let's let our u be negative 2x. So our du is negative 2 dx. So notice that for this, I'm going to have to do some manipulating. I'm going to have to multiply by a negative 2 on the inside and the outside. Okay, so you can see that I'm going to divide this into two integrals. Okay, this first one, negative 1/2 e to the negative 2 times negative 2 dx. Notice how I have gotten this in the e to the u du form, but I have not used u yet. So I can keep with my old limits of integration. Plus the integral from 0 to 2 of 2 dx. Okay, that's easy. So if I want to write e to the u du, then I need to switch these limits of integration by substituting 0 and 2 into my u function. So g of 0 is still 0, but g of 2 is negative 4. So I go, instead of from 0 to 2, I go 0 to negative 4. What's wrong with that? We need to switch those limits of integration. That requires a negative sign, which is cool. It knocks out that negative sign. So now this is easy. So we have this in the form of e to the u du, integrates to e to the u using my new limits. And I'm going to leave it like that and evaluate this part like that. This is old school. We remember how to do that. Here is my function that I am finding the area underneath. From 0 to 2, here's my function, e to the negative 2x plus 2. And I'm finding the integral, which is that area since it's all above the x-axis. Now we're going to evaluate it. Again, 1/2 e to the 0 minus e to the negative 4 plus 2 times, substitute the 2 in, subtract, substitute the 0 in. Doing some aloha. This gives me, remember, e to the 0 is 1 minus e to the negative 4 plus 2 times 2, so that's 4. 1/2 e to the negative 4 is 1 over e to the 4 times the 1/2 gives you this. 1/2 plus 4, 9/2 minus 1 over 2 e to the 4th. So your 5.4 TPs are 11, 35, 41, and 49. See you next time.